All right, now we're going to finish our notes on this. So I'll make it a little bigger. So now we're going to do the square root. You know square root, right? Square root. What's the square root look like? What's the parent function for square root? Y equals what? Square root of x. Now, if you're writing this as a power, not as a root, what power is the square root? It's a fractional power. Huh? X to the 1/2 power. Remember that?
No.
Okay. You should have learned this in Algebra 2.
I actually
For the one person in his class who had me, he did. Oh well. So, x to the 1/2 is the power that represents a root, a square root. Notice it undoes a square, right? So if I was to square that, what do? Remember in Algebra 2 when you have you have something to a power and you raise it to another power, do you multiply the powers? If I square a square root, do I get x? If we do square root of x squared, do we get x? Well, I'm going to write x to the 1/2. I'm going to square it. What do you do to powers when you raise a power to a power? You multiply them, right? What's a half times 2? It's x. So all of the roots are a fraction. So a square root is the root for square, so that means it's 1/2. A cube root is 1/3. It's how we undo a cube. If we want to do a fourth root, it undoes a fourth power, right? Okay, I'm going to graph this first before we try to fill all this in. And I'm going to show you, this is what you should have learned to do in Algebra 1, Algebra 2. Yeah, actually Algebra 1 too, also. In any case, so the square root of 0 is 0, right? The square root of 1 is 1. Is this a sideways parabola? You don't want square root of 2 or 3. Those are not whole numbers. What's the next one? What's square root of 4? What's the square root of 9? And, oops, there's our curve. Yeah? Yeah, that's the curve. Because it is this positive square root. Now, transformation-wise, if we put a negative, if our a was a -1, would we reflect it across the x-axis? And we produce the other arm of that parabola that is a sideways parabola. We'll talk about those later. Got it? Looking at that, are there any values for that function that are to the left of 0? No. Do we have to restrict our domain? When I say the word restrict, that means it doesn't exist everywhere, so we have to tell someone what part of the x-axis applies. What values for x are valid? You can't put in negative numbers unless we do imaginary, and we're not doing imaginary. We're only keeping it real. So if we keep it real, everything underneath the square root has to be positive. So when we go over here, so that do we all see that because of this drawing, we only want the x's that are greater than or equal to 0. Does that make sense? Is that our graph? What about the y's? We only want the y's that are greater than or equal to 0. Yes? No negative values, no negative x's. Yeah? Okay, because we're keeping it real. So how do we write that? How do we write that yesterday? How do we write when we're including 0? 0 is valid. How do we include for a valid point when we're starting our interval? We want interval notation. The bracket. So it's going to be bracket 0, comma, infinity. Open the parentheses, parentheses, right? What's the range? Same darn thing. Is that easy? Easy to remember. Can you just sketch the graph and do it? Remember, if you don't have a 4-function calculator, go get a 4-function calculator for the test and practice with it. Don't wait till the test to get one, because then you won't be used to using the darn thing. Are we clear? Or you could just do it without a calculator because there's nothing on here that you can't do without a calculator. I teach this the way I teach it in Algebra 2, and it's for non-calculator. Okay? All right. So, x-intercepts. Where does it touch the x-axis? Still the origin, right? Because it's a parent function. What's the y-intercept? 0, 0. It's the origin, right? And that's going to be the case until, we start doing transformations. And then will those change based on how we shifted or what we do to it? Okay, in behavior. As long as I'm going to infinity, so that means as my x goes to infinity, what is my y going to? Look at your drawing. Infinity. Can my x go to negative infinity?
No.
No, there is none. There's no in behavior this way. It doesn't exist that way. There is no x going to negative infinity, is there? Unless I do imaginary. Well, even imaginary is not going to work. We're just not going there. We're sticking it. We're keeping real, right? Looking at that, going from left to right, is it going up? Is it increasing or decreasing? Decreasing. So there is none. There's none on the decreasing, yes. And is the increasing interval the same interval it's defined on? It's increasing everywhere, so it's the same as the domain. Is it continuous? No. Okay, let me define this. It's one piece, but it's not continuous over all real numbers. Right, it's the same, it's continuous as long as you're in its domain. Makes sense now? It's not continuous everywhere, so when you're looking at continuity, if it's not all real numbers for the domain, then you need to tell me where it is continuous. And this is continuous, but it's only continuous in that same interval. Yeah? Additional information. Do we agree that this is the inverse of squared? So additional information is that it's the inverse of y equals x squared for x greater than 0. Why did I have to restrict it? Is that the whole thing? If we're talking about inverse, for the inverse of this, it would be including this part down here. But it's only a piece of it. It's only the piece where it's x greater than 0. Now that's the x for this. For the inverse, it's the y. Right? Yeah, well, whatever. Okay, what do we got next? Oh, cubics. Love cubics. Cubic. So, do y'all know why it's called square and cubic?
No. Second dimension.
Yeah, square. If something is squared, for a square, are the dimensions x squared? If you're saying x is one side, if it's a square, is x the other side? And so is the area x squared?
Yeah.
What about a cube?
3 squared.
Yeah, because it's a length, a width, and a height. Do y'all see that it's three-dimensional? So just for you understanding where this all comes from, so it's a little easier. Remember, if this is x and this is x, the area is x squared. That was like for a square. Oh, that actually goes, hang on. That goes on the square one. I thought about that yesterday and wondered if y'all knew why this was called what it was. This one. Look at your quadratic. Is this a square that is x by x, so its area is equal to x squared, and is that where squared functions come from? Whereas cubics come from 3 dimensions. Do you know how to draw a 3-dimensional figure? You just put dimension into it like this. Those in architecture probably can do this. All right, so is this x and x and x if it's a unit cube? So is that x cubed? So it's volume this time. Volume equals x cubed. That's where this comes from. And the parent function is y equals x cubed. We'll transform them later, but right now we're doing parent functions. Okay, do you know what it looks like? It's the one that squiggles. It's the S-shaped one. Oh, y'all look at me like I lost my mind. All right, So here we go. Now we're going to do the stinking table because y'all are like looking at me like I've lost my ever-loving mind, but that's nothing unusual. Okay, you're going to do X and Y for my favorite numbers, and then you're going to add a few. My favorite numbers are -2, -1, 0, 1, and 2, but I need to go a little more for this one. We're going to do -3, -2, -1, and 0, and then I'm going to do another one just because I don't have room. And this one's going to be 1, 2, 3. Okay, so -3 cubed means it's -3 times -3 times -3. What's -3 times -3? Times -3, -27. This is equal to x cubed. That means I'm taking the square and I'm multiplying another negative to it. So all the squares are going to give you a positive number, right? And then you add it, and then you multiply by a negative number. All of the negative x's will have a negative y, because it's a negative times a negative times a negative, right? So what's -2 squared? -2 times -2. Random number generator. 4, right? What's 4 times -2? -8. You need to know your cubes to at least 3. It would be nice if you knew them further, but that's okay. -1 cubed. -1. Oh my Lord. What's 0 cubed? 0. Okay, on the ones, are they the same values, but now they're positive? So it's going to be 1, 8, and 27. So for the cubic, once you get the negatives, do you just, all the positives, make them positive? I'm positive you make them positive. Now, we don't have a y of 27, do we? No, it would have been nice. So my favorite numbers would have worked for you, but I just wanted you to practice. So what are we going to graph? We're going to graph -2, -8. And we're going to graph -1, -1, and 0, 0, and 2, 8, oops, and 1, 1. Do y'all see it now? It's the one that looks like an S. And before we're done with this, you'll be doing the function dance for me.
Is this tangent?
No, this is not tangent, but it looks a lot like it, doesn't it? The difference is for this, it doesn't have asymptotes. So even though it's long and skinny like that, it does go on forever and ever. So eventually you will cover all the x values. You just have to go a really long way, right? So a big X gives you a humongous Y. Yes? Does everybody have their graph?
No.
Why not?
Oh, yeah,
Oh. Love you too. Here we go. Domain. Look at that. It's going to go on forever and ever. Is it going to go on forever in the x direction also?
Yes.
So what is the domain? Huh?
That inside.
Yes. Because saying all real numbers is not sufficient anymore. You need to be very specific. It needs to be from negative infinity to infinity. I need y'all to learn that now. What's the range? Negative infinity to infinity. What's the x-intercept? 0, 0. What's the y-intercept? 0, 0. Awesome. In behavior. As x goes to infinity, now answer it. Y goes to? What were we saying?
Negative.
No, it's going to positive. Yeah. Okay. As x goes to negative infinity, what does y go to?
Negative infinity.
Yes. Are all the odd functions like this? X to the 5th. Because did y equal x do the same thing? Remember I said all odd functions a long time ago? Anyway, back when we did even and odd with trig, I mentioned it. But all the odd, if it's x to a odd power, just x equal to an odd power, it's going to have the same end behavior. They're all going to have that same shape. There's just going to be more squiggles in between. All right, increasing or decreasing, what do you think? Huh? Do you read from left to right? I do. Read from left to right. That's the way we read. We're not reading.
Increasing.
Yes.
Is,
So it's the whole interval, right?
yeah, like a negative.
There are no decreasing parts. Once we transform it, will there be? Oh, yeah. Are there any decreasing? None. Not for the parent function. Continuity. Is it continuous? Over what interval?
3.
Oh, Lord.
27, -22.
Does it keep going on forever and ever? Can I put any number I want in there? So is it continuous over the whole interval?
Yes.
The whole domain, so it's negative infinity to infinity. You are defining the domain over which it is continuous. So it's continuous on that interval.
This is hard.
No, it's not. You're making it hard. And it's because it's been a long time for you and you don't remember anything. But it's going to be okay. We're going to be going over this and over this and over this. Right now I just need to establish a basis to start adding to it. Okay, cube roots. So are we undoing, with the root, are we undoing the cubic? So if a cubic is the third power, what's the fraction that undoes 1/3? So this is y equal x to the 1/3 power. Which another way to write that is that root. See, this is the root sign. You put a little 3 here and an x. Is that how you show a root? Are we going to do the 1/3 power because we're not done with this stuff and we're going to have to use that 1/3? Yes. Okay, let's draw this puppy. So this is the inverse, just to start with. This is the inverse of a cubic. So what does a cubic look like? So are we going to flip things? Yes. Can you take a cube root of a negative number? Yes. It's not square root. You can take a cube root of a negative number. So now we're doing the exact opposite. So we're going to make a little XY table over here. X. We're going to put my favorite numbers in it. But remember, we're switching. So this time we're going to put in the y's and get an x. My favorite y's in this case are, because it's the inverse, it's -2, -1, 0, 1, and 2. Because I'm keeping it on the scale now. I'm not messing with it anymore. So remember that this is the cube root of this. So if I take this and do it, what's -2 cubed? What's -2 times -2 times -2?
-8.
What's -1 times -1 times -1? That's 0. This is 1, and this is 8. Let's go through this. How did I do that? I didn't want to do cube roots. I wanted to cube. So whenever we're doing the inverse, you just put the numbers in y and then undo it. So if I go -8, do cube root of it, do y'all have to memorize that it's -2? Y'all remember that 2 cubed is 8. You got to remember that 8 cube root is 2. So let's graph it. So I got -8, -2. I get -1, -1. I got 0, 0, 1, 1, and 2, 8. Is it just the sideways of what we just did? Because when we do inverses, what do? We reflect across what line? Y equal x. So if we put those two graphs together, would they reflect across the line y equal x? They would. Because remember, inverses, do we swap the x's and y's? So if you can do the cubic, could you have just taken those and flipped the points? Switch the x's and y's to get this? Is that the easy way to think about it? Everybody okay with the graph? Excellent. Okay, looking at that graph, just look at it. What's the domain? Yeah, negative infinity, infinity. What's the range? Same thing, are all real numbers. But now we don't write all real numbers. We got to be more specific. We have grown up, hopefully. Some people have. Not Jerish yet. He's going to work on it for me. Maybe. Maybe before he graduates. Yeah, I can dream. I am delusional. It's okay. I'm used to it. Does it go through the origin? So what's its x and y intercept then? 0, 0, because this is the parent function that makes it easy. Once we start shifting this around, is it going to be 0, 0 anymore? Nope. But let's start at 0, 0, and we'll do our shift to figure out where we're going, right? If you start with the parent functions, you know the parent functions, is this easy. So that's why we're taking 2 days on the parent functions. Okay, in behavior. As x goes to negative infinity, what does y go to? Negative infinity. As x goes to positive infinity, what does y go to? Positive infinity. So they're still going in the same direction. So as I go, x goes to positive infinity, my y goes to positive infinity. As x goes to negative infinity, my y goes to negative infinity. Does everybody see it on the graph? Is this function increasing or decreasing? Does it change? It doesn't change, so what is it? Increasing? There's none on the decreasing intervals. In our increasing intervals, it's the same as the domain. It's from negative infinity to infinity. What about continuity? Is it continuous over the whole domain? Yep, it is. Now, additional information. What is the invert? What is it the inverse of?
Function.
Y equals x cubed. Are there any restrictions? Is there any piece of the domain that doesn't work? No. For cube root, it's easy. It's all real numbers. It's the whole domain. Okay. And for our next trick, here comes the fun stuff.
Oh, come on.
Okay. Exponential functions are y equal to some base raised to a power. Now, what's my most favorite one is y equal e to the x. Why? Because we use it in calculus all the time. And I want you to know what that graph looks like. Boy, do I want you to know what that graph looks like. In the worst way, I want you to know what that graph looks like. So, but in Algebra 2, we started with a specific one. In Algebra 2, we started with y equals to 2x. Do y'all remember that? Well, it makes it easy. We're gonna use this one for right now. But they all work the same. If it's e to the x, it still works the same. Okay? So what we do is, that means I've got 2. When I put in an x value, that means I am doing that 2 to that power. So let's do the positive ones first. We're going to make a little table over here. We're going to do x and y. And we're going to do my favorite numbers. We're going to do -2, -1, 0, and then I'm going to make another table here to make it easy. 1 and 2. Let's start with 2. It's an easy one. Remember, my y is equal to 2 to the x power. What's 2 squared?
4.
4. Oh, that means we can do 3 easily. We probably need another point. What's 3? So it's 2 to the 3 power. What's 2 cubed? What's 2 times 2 times 2? 8. Okay. Are we playing 2048, by the way? When you have a 2, it's just a 2. 2 to the 1 power is 2. 2 to the 0 power. What is anything to the 0 power? 1. By definition, anything to 0 power is 1. All right. The negative powers. Does that mean, because remember, if you have a negative power, can you make it positive by moving it? If it's in the denominator, move it to the numerator. If it's in the numerator, move it to the denominator. Remember, you flip it. Okay, so does this mean that it's 1/2? Because it's a negative power, instead of being a 1, which is a 2, it's a 1/2. So if I do -2, is it 1 over whatever 2 squared is? So is it 1/4? Are the negative powers going to get really tiny? Yeah. So how do you graph this? 1/4. That's 1/4. It gets infinitely small. It's approaching 0. Is there an asymptote there? Yes. By definition there is an asymptote right here. It never gets to 0 because it's like taking something and you cut it in half, and then you cut it half it again, and you cut it half it again, and then again, and again. Well, you get infinitely small, but you'll never make it go away. You'll never reach the wall if you take half of the size of the step you took previously. You'll get closer and closer and closer, but you'll never get there. That's the point.
That's the point.
That is the point. Yes. Awesome. All right. So at 0, on all of these bases, is that a common point? If I do 10 to the x power, if it's 10 to the 0, is it still 1? Do all of the bases, the parent functions for all of the bases, go through that point, 0, 1? Is that how you sketch them all? Now 2 is easy because at 1 it's 2, at 2 it's 8, here it's a half, here it's a fourth, and from that shape, can we see that it, from this side, it's going closer and closer and closer to 0, but it's never getting there, and this is going up and to infinity and beyond. Is that the general shape of every single one of the bases? So when you're doing e to the x, guess what? You are literally just going to put 0, 1 on the graph and go whoop. You're going to swag it in. Really, really. You're just going to whoop. With 2, can we put points on there? With 3, could we put points on there? Anything else, points are off the graph. Don't worry about it, right? Whenever it's a number, based on number, what I want is the ones that you absolutely have to do with the base, you have to absolutely do these. Can you at least do those? Yeah. If it's 4, can you graph 1, 4, and then 1/4? Just show that it's really tiny. Do you understand what I'm getting at? So the points that you have to show on the bases every single time are these 3, and then from those 3, can you tell what the curve looks like? If it's something like 2, this one, the one I started with, can you show me more points? Yes, you can. And do I expect you to show me more points?
Sure.
I do. Looking at that, does it go through the origin anymore? No. Does it have an x-intercept?
Nope.
If the x-axis is the asymptote, does it ever touch it?
1, 0, 1.
Huh?
Oh, never mind.
Yeah, you said y-intercept. You're telling me y-intercept. What is the y-intercept? Say it again.
0, 1.
It's 0, 1. So my y-intercept this time is 0, 1. And we don't have an x-intercept because we have a y-intercept. I mean, but asymptote. I'll get there. So what was that domain again? Looking at that, are all the x values possible? So what's my domain? Okay, what's my range? Can 0 happen? No. So I start at 0. Am I including that point? No, so it's a parentheses, not a bracket. Got it? 0's not included because it's an asymptote. And is it going to infinity and beyond? Yep. Yep. Everybody okay with that? In behavior. This is going to be fun. This is a little different. As x approaches infinity, what is y going to approach? No. Infinity. As my x goes to infinity, what's my y going to? As my x goes to negative infinity, what's my y doing? Y, what's it approaching? But never getting there? 0. So on my in behavior, so let me finish this one. This goes to infinity. But as x approaches negative infinity, my y is going to go to 0, but it's never going to get there. Is it? Nope. Okay. For what we see, is it continuous? Yeah. What's the domain it's continuous across? The whole domain, right? The y is not defined everywhere, but for continuity, we want to know the x. So this is the same as the domain. And there are no decreasing. Oh, wait. It's increasing it. Yeah, increasing in continuity. I didn't write it down. Increasing continuity, R. And then what's the additional information? This is where we write asymptote. Oops. I can't spell. I can't talk and write today. Oh, I did it wrong. Y equals 0. X-axis, which is y equals 0. Yes? That wasn't bad. Is it going to take practice? Because y'all probably did this all at the calculator when you were in Algebra 2, and I don't find that acceptable anymore. I'm going to make you do this by hand. Which means you have a 4-function calculator. Is a 4-function calculator going to help you fill in the table, but it's not going to graph it for you. You have to graph it. Capiche? And I'll give you some practice on that Monday. We'll probably have a quiz over it by Tuesday. So plan on quit. So do something this weekend so you can actually pass the quiz. All right, moving right along. Logarithmic. Oh, what fun. This stuff's fun, right? Yeah. Okay, for logarithmic, my favorite one, of course, so let me actually right up here, before we go any farther on exponentials, my favorite is y equals e to the x. That's my all-time favorite. It's the one we use in calculus. It's the one they don't know the graph of. Real quick, I want to show you how easy it is to graph. Do we all agree that anything raised to the 0 power is 0? Is 1, sorry. So is this point, that's 0, 1, is that point going to be on every single, remember I said it's going to be every single base? E is irrational. It's not a nice number. So here's what you do when you graph it. You just have to realize it's shaped the same way. It's going to approach 0, and it's going to go to infinity, and you are done. You have to have one point on there. That's it. That's the only point you need to graph. Do I expect you to be able to graph that? Yes, it's going to be on your test. I promise you, I will make you graph that on your test. Can you all graph the point 0, 1? Can you all swag that in? You're going to 0 as you go to the left. You're going to infinity as you go to the right. Make a nice smooth curve. Can you all do that? Then you just got full credit on the test for that problem. I promise you will see it. Now, my favorite log is y equal natural log. Guess what its inverse is? E to the x. Why do I love them? Because they're all over calculus and they are inverses. You want to know what its graph looks like? If it is an inverse,
Is that an H or?
it's an ln, natural log. ln. So on this one, if it's ln, it's the inverse. So instead of 0, 1, guess what you're going to graph? 1, 0. And instead of the x, as x approaches infinity, y approaches 0. Now, as y approaches negative infinity, x is approaching 0, like so, and like so. Is that the only point you need to have on the graph? And that point means that natural log of 1 equals 0. Let me write that a little neater. ln of 1, that's the one point you need to know. Is that the inverse of the exponential of 0? E to the 0 is 1. Natural log of 1 is 0. They are inverses. You need to know them. That will be a question on the test. I will ask you what the natural log of 1 is, and I will ask you to graph that. Are we clear? Those are really, 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 if you understand those graphs, calculus is so much easier. If you don't know those, and it's not even just engineering calculus, it's not just STEM calculus, but business calculus, they use exponential. You understand how the money works? Interest rates? Oh, how about exponential growth of bacteria in a petri dish? Actually, it's logistic growth, and that's second semester calculus. But first semester, we talk about exponential growth, which is e to the x. All right, this equation, the base one is we have some y equals to log some base of x. Guess what natural log is? It's log base e. This is the same as saying log base e of x, but we don't write it that way. We always write this, but that's what it is. It's the base e. So and before, remember how we did 2 to the x?
10, right?
Huh?
You use 10? Or is this not that?
No. If I don't write anything, if I write y equals log x, guess what I'm not writing because I'm being lazy? 10.
Yeah.
Remember that? Yeah, you did learn something. See?
No?
We use base 10, right? We like base 10 as our number system. But you know that in computer science, they like base 2. It's called binary. Computers speak binary. Base 2. Yeah. I can write any number in terms of 0 and 1, and that's what the computer does. computers are real simple. All they know is 0 and 1, but we could do so many amazing things with 0 and 1 if you understand math. There's amazing things you can do with it. Okay, so it's the inverse. So I already drew one natural log. Do all the logs look like that? They do. Every stinking one of them goes through 1, 0. Every one of them. So every single one of them is going to go through that point right there. If it's 2, because if suppose that we're going to do what we're going to do for our graph. This let me erase this. For this graph, we're going to graph. This is going to be y equal log base 2 of x, because we're doing the same as, so this one up here, this one we just did a minute ago was y equal 2 to the x. The logs undo them, so this is the inverse. So see how this graph does this? Are we going to switch the x and y's? So the easiest way is to take this table. Can we take this table and switch the x and y's? That's what we're going to do.
Oh, yeah.
Oh, yeah. That's right. So when we switch our x's and y's, from up here, I had 1/4 -2, so here I'm going to do 1/4 -2. Up here, I had -1 1/2. I'm going to do 1/2 -1. Up here, I had 0 1, so I'm going to have 1 0, and then I had 1 2. I'm going to have 2 1, and I'm going to have 8. See how it's 8 3? I'm going to have 8 3 3 8s 8 3. You'll see what I did. All I did was switch them. Is that how we do inverses? So additional information. This is inverse of y equals b to the x for the base one. So if we graph this, notice as x get closer and closer and closer to 0, is y going to get smaller and smaller. So we're just going to do 1/4 of it, and we're going to go down to 2, and we're going to do 1/2, and we're going to put it at 1, -1, and then at 2, at 2 of the y, we're going to go out to 8 on the x. So does this look like that other one where now it's approaching a y of 0 instead of an x of 0, and is it, so where's my asymptote this time? What kind of asymptote? Last one it was a horizontal asymptote. I forgot to write that. This asymptote, that's a horizontal asymptote. Ha! What kind of asymptote do we have this time? Vertical. This is our asymptote. Yeah, so it's x equals 0. Asymptote at x equals 0. Isn't that a cool graph? They're really handy. It's really handy to know. Natural log is all over the place. We have to understand it. So this time, can x approach negative infinity? Huh? Where's that asymptote? Horizontal asymptotes you can cross, but we didn't cross it on the other one. Verticals, you cannot cross it. We can't cross that barrier. Natural log does not exist on the other side. Absolute value does, but not natural log of x. So there's none. It doesn't exist on that side. Does it only exist? So what we're going to say is, as x, oh, I forgot, I got to change colors. As x approaches infinity, what does y approach? What's it going to? It's really slowly, but is it going to infinity? Okay. So the only behavior I have is as x approaches infinity, y approaches infinity. All right, looking at that graph, what's my domain? Do I have any x's less than 0? Do I have an x at 0? Larissa, do I? Can x exist at 0 for this graph?
No.
It's an asymptote. So my domain, does it start at 0 and go to infinity? What about my range? Can it be any number for the y? Do y'all see that? Any number for the y. So what's my range? It's still negative infinity to infinity. Do I have an x-intercept? Does it ever cross the, oh, that was interesting. Does it ever cross the x-axis? Yes. So what is it? What was it again?
1, 0.
1, 0. Do I have a y-intercept? Did it ever cross the y-axis? Nope, none. Is it increasing over the whole interval? Do you see that it's increasing over the whole interval? So is it the same as the domain? 0 to, oh, okay, that was a really weird comma, sorry. Zero to infinity. Is it ever decreasing? No, none. Is it continuous as long as I restrict the domain? As long as I define where it's good. Can I say it's continuous when it's less than 0? No. Where is it? Where do I draw it and not pick up my pen? Over here in the positive x's. Can't be a 0, can't be a negative. So do I have the same interval for continuity as I do for the domain? And increasing. It's not defined anywhere else. We will finish this on Monday.